Okay everyone, in this lecture we're going to be talking about metal semiconductor junctions and diode capacitance. There are two pictures of the day today, and what they have to do with the lecture is opposite for each picture. So the first picture here, kind of look at this and see what do you think is happening here. What is this picture of? Well, this picture is something you don't want to happen. So imagine you're walking down the hallway or walking through a lab in winter, and you build up a lot of electrostatic static electricity, and you touch one of your devices in the lab, and you basically put on it thousands of volts. And so this is what happens when that electrostatic discharge hits the device. This is a metal line here. This is an insulator coating here on a semiconductor wafer, and this is a conductive area of the semiconductor. And what happens, the voltage becomes so large that basically you got a lightning bolt here, which pulled the metal line over across here and then froze it and made a permanent contact between this metal line and semiconductor region. And so one of the topics we're going to talk about today are devices which are used to help prevent electrostatic discharge. And here's a device that is the opposite in that it is made to withstand very high voltages. And so this is a 1600 volt silicon carbide Schottky rectifying diode. And that's related to our first topic, metal semiconductor junctions. And so some of the highest voltage rectifiers made with semiconductor devices are not PN junctions, but metal semiconductor junctions. So we'll learn more about some of these things today. So let's switch gears now. So up until this point, we have assumed that our metal contacts were just on the semiconductor material and we've really ignored them, right? And so I've got my PN junction, I put a metal contact, and I assume that this works great at getting electrons back and forth, and this works great at getting holes back and forth here. And remember, when we join two different semiconductor materials, such as P-type and N-type material, some really interesting things happened. And we know that metals are even more different than semiconductors, right? So when we join a metal and a semiconductor, something interesting might happen as well. In fact, we'll see it can create a diode. And the type of diode it creates is called a Schottky diode, named after a lot of the early theory that was developed by Schottky. His first contribution was basically looking at the energy required to rip an electron off a metal and emit it into vacuum. And you'll see why that's important today, because you'll see that energy required show up in how we calculate the diode features for a Schottky diode. So a little bit, why do we care about this type of diode? Well, there are two reasons why we're going to care about these metal semiconductor or Schottky diodes, and that name is used interchangeably. You either say metal semiconductor diodes or Schottky diodes, it means the same thing. There are two reasons why we care about this type of diode. First, it's really easy to make them. And that's especially important with exotic and wide bandgap semiconductors such as silicon carbide and gallium nitride, because with silicon carbide and gallium nitride it is very difficult to do p-type doping. And so they can make n-type silicon carbide and n-type gallium nitride, but if you want to make a diode, it's hard to make the p-type version. And so what they'll do instead is they'll make a metal contact that makes a diode, and then they can start making devices with these very high performance material systems. Why else do we care? Well, sometimes when I have a metal contact to a semiconductor, I don't want a diode contact. So in this case, I'm assuming that this contact flows electrons freely and it has no rectifying behavior, and same for the contact up here, no rectifying behavior. So that's important. And so we need to understand how can we design these contacts to be rectifying, like a diode, or how can we design them to be what we would call ohmic, meaning it just acts like a very low resistor. So, Schottky barrier diodes are made from a junction of a metal and a semiconductor. And there's a couple terms that are very important to understanding Schottky barrier diodes. The first term is the metal work function. The metal work function, phi sub m, multiplied by Q, because phi sub m is a voltage multiplied by Q, gives us an energy, right, in electron volts. And it is the minimum energy usually measured in electron volts to remove an electron from a Fermi level in a metal to a point infinite distance away at the vacuum level. So what this means is, let's say I have a chunk of metal here, and I want to rip an electron away. Basically, how much energy does it take to rip an electron away from the metal and pull it far enough away that there is no interaction between force trying to pull it back to the metal? And so that's called the vacuum level. It's kind of like pulling it in outer space. You pull it far enough away that it doesn't want to go back into it. So that means you've basically exhausted all the energy required to pull it away from the metal. And typically for materials like aluminum or gold, you can see the energy required to rip an electron from the Fermi level all the way outside the actual metal is in the range of 4 to 5 electron volts. The next term we need is a semiconductor work function, phi sub s. So we had a metal work function, now we've got a semiconductor work function multiplied by Q. Potential times Q gives us electron volts, which is energy. And it's the energy level from the vacuum level to the Fermi level in a semiconductor this time. So same thing, imagine this is a semiconductor. How much energy will require to pull an electron out of the chunk of semiconductor far enough away that you've basically, it will not come back to it. Essentially, you've taken all the energy required so that there's no longer any attraction between the two. You've taken all the way out into the vacuum level. The next term is electron affinity. It's the vacuum level, meaning pull it all the way out of the material, to the conduction band, not the Fermi level, but now the conduction band, and we'll call that chi here. Okay? Now, remember that the Fermi level at 0K in a semiconductor is the midway point between the empty and filled states. Okay? For a metal, the Fermi level is the same thing. The only difference is, for a metal, there's no band gap. So we'll see that here on the next slide. So hopefully this starts to become a little clearer now. So let's start to build up a metal semiconductor junction. So here is my metal. Here is my semiconductor. This is the vacuum level, meaning this is electrons outside the material floating freely in air or basically outer space. Okay? And so you've got the vacuum level. Here's my Fermi level for the metal. Here is my metal work function, the energy required to take an electron from the Fermi level in the metal to the vacuum level. And then for the semiconductor, I've got my conduction band, my valence band. Here's my semiconductor work function, energy required to take an electron from where the Fermi energy is, rip it out of the material to the vacuum level, and then I have my electron affinity here, which is conduction band to the vacuum level. Okay? Now, to form a Schottky barrier or a diode with N-type material requires that phi sub m is greater than phi sub s. The metal work function is greater than the semiconductor work function. You can see that. This energy is greater than this energy. And so let's put this together and let's join the metal and the semiconductor, and you can tell me, what's the first thing that must happen in the diagram below? Anytime we join p-type and n-type material, ask yourself, what always has to happen? Well, if you've thought about this and you've answered it correctly, you'll say that the Fermi energies have to line up, right? The other thing that we're going to notice here is that the metal has a ton of electrons, right? So it's like N++++. So knowing that how doping affects depletion width, on what side of this, as this joins and forms a diode, will all the depletion and band bending be? Well, remember the depletion dominantly happens into the weakly doped side, and so if this is acting like heavily doped because it's a metal, then all the depletion and band bending will show up on this side. So let's pull this together and see what it looks like. So remember, again, the metal has such a high density of electrons that it acts like super heavily doped, so there's no band bending. And here is my starting condition. The Fermi levels have to line up, and look what happens here. Here's my metal. Here's my semiconductor. Okay? I get a depletion region, and if you look at the band diagram, what I've done here is I've lined up the Fermi levels. The semiconductor had to shift down for the Fermi level to match up. It had to shift down, and so this comes down. And then you have to still connect the bands, but you can see the band bending now goes like this, and it's all on the semiconductor side. if you're looking at how do I know how much this bends up here, well, the original offset I had between the bands, so if I have this here for the change in energy from here to here, I need to preserve it over here, same amount. If I have this here, meaning the valence band is this much below the Fermi level in the metal, then where I actually join them together, you have to maintain that. And so I start with these points to begin with, okay, as I draw this, knowing that I have to maintain that same offset between the valence band and the Fermi level in the metal and the conduction band and the Fermi level in the metal. And then I know I have to shift the Fermi level down, so I've done that here, line it up. And the last thing I do is I basically take the shifted bands, right, and I connect them to these points with this curved line here and end up with this diagram as follows. Okay? So let me erase this and let's explore this in greater detail and see if we can start to figure out how this thing works. Okay, so we've joined our bands together. We've got our band diagram. Notice here that I've got a contact potential. And remember, contact potential is how much the bands had to bend when you join the p-n junction together. Same thing here. My contact potential, V naught, is equal to the difference in the metal work function and the semiconductor work function. Here's the metal work function. Here's the semiconductor work function. The difference between this and this is the difference in the Fermi level positions, and therefore it's the amount of bending it had to come down, and therefore it is my contact potential. The other thing you notice here is I've got this barrier, phi sub b here, and this is going to block electrons trying to come here, and that's important as we try to understand why this will have rectifying diode behavior. And so I've got phi sub b here, and that's easy to calculate as well. It will be phi sub m minus chi here. Okay, so you could see that the height here, right, should be the difference from here to here, right, this difference here. Well, that's just this minus this. And so this is why I care about this term, electron affinity, because it helps me calculate this barrier height here. So what you're going to find, well, one more thing I'll explain first, is notice I have a depletion region here. Anytime I have bent bands, what's that mean? That means electric field, right? Anytime I have electric field, the free electrons are swept out. So the electrons are swept out this way. Notice that when this thing joined and I depleted, I end up leaving behind these phosphorus atoms that have positive charge. And so on the other side, I see the need to have the exact same amount of negative charge show up so that I have charge balance on both sides of the junction. However, all the depletion region width, again, is into the lightly doped side, which in this case is the semiconductor. So what we're going to find is that this thing will give us rectification, but it'll be based on electrons only. We'll talk about that more on the next slide. And I want you to notice also that basically this looks like half of a p-n junction. And so we can treat this when we derive equations for it basically as half of a p-n junction in terms of the equations we might use. Okay, so let's start to understand current flow in this. So now I'm going to put my metal semiconductor junction in a circuit and apply voltage and try to understand why it gives me diode-like behavior. Okay? So let's look at this case here and let's put positive voltage on the metal side, and what will happen? Well, we know that when you put positive voltage on any kind of band, metal or semiconductor, it brings the bands down, right? And so here I put positive voltage on the metal side, negative on the semiconductor side. Positive brings down, negative brings up. And look what happens here. At this point, positive voltage, I start to get a significant amount of current flow because the very high concentration of electrons I have here, remember this is N-type material. This is N-type material, the Fermi level is close to the conduction band. This very high concentration of electrons starts to spill over into the metal, and I see an exponential increase in current because I'm tapping into an exponentially increasing number of electrons as I get closer to the conduction band edge. Remember, because of the Fermi distribution, the density of electrons increases as you get closer to the band edge and then density of states brings it down. But you never, as we said in the previous lecture, you never get to that point. Okay? Let's erase this here. Whoops, it's moving stuff around. Sorry, hold on a sec. Well, I'm just going to keep going on this. Okay, so in this case, positive voltage, we get a lot of current. Okay, Now, let's look at the case for negative voltage applied to the metal side and positive to the semiconductor. Negative voltage raises the bands up, positive voltage brings the bands down. Now, what's happened here is my electrons, I have a ton of electrons, they are no longer going to make it over to this side because it requires way too much energy for them to jump up here and diffuse over. Okay? However, what about the holes? Well, if you look at this, I still have minority holes that are generated as an electron is created by thermal generation. A hole shows up, it can move around, and if it's close enough to the edge of the depletion region, it can go across as drift current. And so lo and behold, when I put this bias on it, I get a constant but small reverse saturation current just like a diode, and it's the same type of current in a diode. It's drift of minority carriers in reverse bias here. Okay? Last thing I'll note before we go to the next slide, if you want to look at the total amount of energy you have here in terms of the barrier height, you just basically add the voltage you're applying, reverse bias voltage plus the contact potential. And in this case, we forward bias, we reduced the barrier, so it was a contact potential minus the applied voltage. So let's take a little bit to summarize what we learned. So, to summarize, for a N-type Schottky diode with the case of the metal work function greater than the semiconductor work function, I get diode-like behavior, and in forward bias, I get electron diffusion into the metal and hole drift current. So I've got forward bias, positive voltage on this side, electrons diffusing over this way because I'm tapping into there and they see a high concentration here. They see no electrons here at this energy level, so they diffuse here and then they'll give their energy up as they go down here. But the point is, tons of electrons spilling over. And under forward bias, I still have holes that are thermally generated here, drifting across, but this is really small. So I don't worry about the drift current. I assume that the diffusion current dominates. Under reverse bias, I build in a huge barrier for electrons to try to jump over here. So the electron current disappears. And all I'm left with is the thermally generated holes near the depletion region edge, which move in this direction. And remember, just like reverse saturation current for a regular diode, this amount of current does not change with voltage because it doesn't matter if they have to fall off this far versus falling off this far. Once they fall off the cliff, they make it to the other side. So the limiting rate is the thermal generation rate. It's not the applied voltage, and hence I get a constant current with reverse bias. The last thing I'll note here is that you might look at this and say, well, if I put all this negative voltage on this side here, shouldn't I basically be repelling electrons to go this way? Well, the key thing that we designed for this that made it work well is this barrier height phi sub b. As long as phi sub b is large enough, then electrons will not have enough energy to jump over this barrier and go in this direction and give us current flow. And so a key requirement for a well-designed Schottky diode is also that this barrier height for electrons in the metal is large enough that they can get enough energy to jump the barrier and go over into the semiconductor. And we can calculate that from quantum mechanics. If you have you take in the Boltzmann factor and you calculate your reverse saturation current due to electrons. So I know I have a reverse saturation current due to holes, but the reverse saturation current due to electrons trying to jump over this barrier is proportional to e to the q phi sub minus q phi sub b over kt. So as your barrier gets larger, your chances go down exponentially. Well, that's easy, right? Because if we looked at our energy distribution for electrons, it always has an exponential type energy distribution based on the Fermi distribution. All right, now let's go on to p-type semiconductors. And in this case, I'm going to have phi sub m less than phi sub s. That's important if I'm going to make a diode with a p-type semiconductor and a metal. So phi sub m is less than phi sub s. And so I have to do the exact same thing. I need to line up the Fermi levels, right? And so you can see that over here I've lined the Fermi levels up. At the interface, I need to maintain the same delta EC and this same delta EV with the Fermi level. And so I maintain that energy there, and I maintain the same amount here, right here at the interface. Okay? And then I have to shift the bands, and so basically this has to shift up by that much, and so this all shifted up, and so that puts my bands up here like this, right? And the last thing I do is I connect the area of the shifted bands with the offset here at the interface, and note that the metal is heavily doped and the semiconductor side is lightly doped, so all the depletion happens in the semiconductor side. Okay. So, let's see if we can figure out how this thing works now. Whoop, I'm sorry. Let me, okay, technical difficulty here. So let's see if we can figure out how this thing works. So, let's say for this one that we put positive voltage on the metal, okay? If I put positive voltage on the metal here, this band has to go down, right? And so if I put positive voltage on the metal and this shifts down, then these will be even bent even more. It'll be like this, right? And this will be like this. Well, if you look at the current that can contribute, when you put positive voltage here and this shifts down, the only current I have is electrons, which are thermally generated here, which move around, wiggle, and fall off the cliff edge. And so for the case of positive voltage for this device, if I'm drawing an IV plot here, if I had positive voltage applied, I would have, with that positive voltage, a constant and small current. Okay? So let me label my diagram here. Here's current versus voltage. Okay? Now, next let's apply negative voltage to this device. Negative voltage is going to shift this band up. When that happens, that's the same as shifting this down, right? And so right now I've got a barrier like this, and I've got a ton of holes here because this is p-type material. Well, look what happens here. As this shifts down and becomes like this, all of a sudden I can have holes spilling over to this side, and I get a ton of current. And so what you'll see is that you get exponentially increasing current for negative voltage for this case. And so again, you get diode behavior. The current is in the opposite direction of how we conventionally assume voltage and current for a diode, but importantly, it is rectifying as well. Okay? Notice also I get the same depletion region width, negative charge on this side because these are boron atoms that are uncovered, and I have to have positive charge showing up on the opposite side for the metal. Okay, let's look at one further case. So we've talked about how to make a diode with N-type material. We've talked about how to make a diode with P-type material, but what would be a third case? Maybe where I don't want a diode. Okay? So here is a metal and a semiconductor, but now I have phi sub s greater than phi sub m. Phi sub m is less than phi sub s. So I'll do the same thing. I'm going to join them together, maintain the offsets at the interface, and so here's the offset there, and then here's the offset here, so I've maintained that offset. Erase these real quick so I don't mess this up too much. And I line up my Fermi levels, you can see that as well. And look what happens here now. I've got a ton of electrons here. This is N-type material. I've got a ton of electrons here. This is a metal. So for this type of device, you'll notice there is no barrier for electrons shifting this way or this way. As I put voltage here and shift this up, or put voltage here and shift this up, you'll spill electrons back and forth freely because there is no barrier here to prevent them from moving back and forth as you apply voltage. And so, what would the IV plot look like for this thing? Well, if I were to plot my current versus voltage for this, you would find that this is what we call an ohmic contact, meaning you'd have a linear response of current to voltage. And this is a critically important contact for devices, because if you don't have ohmic contacts, if I have a laser or a MOSFET or a BJT or some of these other devices, I need to make metal contacts to those devices, and I don't want rectifying diodes all over the place because then I can't get current flow through the device. And so ohmic contacts are critically important when you need to inject carriers into a semiconductor without it being rectifying. Let's look at another type of ohmic contact. Let's assume that it is now p-type, so p-type material, and phi sub m is greater than phi sub s. Same thing, maintain the offsets here at where you actually join the material, right where you join the material. Line up the Fermi levels. This has to shift down, put the band bending in the semiconductor side. You can see that the electrons have a barrier to diffusing over here, but it doesn't matter. There are barely any electrons because this is p-type material. I've got a ton of holes here, right? And so now I can basically move holes back freely from one side to another and basically get current to flow either direction. If you get confused about having electrons here and holes here, don't worry about it too much, because if I put a hole over here, it's basically, it can recombine with an electron over here. If I inject an electron over here, it could recombine with a hole. And electrons and holes are kind of the same thing, aren't they? Because the hole is just the absence of an electron. And so on this side, you're moving electrons back and forth. On this side, you're moving the absence of an electron back and forth. But the main point is that you've got a ton of absence of electrons or tons of holes, tons of electrons. And if you put voltage and shift the bands on either side, there is no barrier to prevent current flow, and therefore you get an ohmic contact for this device as well. Here's one more way to make an ohmic contact, okay? And this is important because sometimes for some semiconductor materials, you can't basically get semiconductors with the right work functions for the semiconductor and the right work function for the metal to give you an ohmic contact. So this is a way to cheat a little bit, but it works really well. And so for this case, we had semiconductor and metal work functions such that we get a Schottky diode or rectifying behavior for a metal and N-type material. And so here's my barrier that I have for a high concentration of electrons to diffuse over this way. But I changed it somehow. And how did I change it? Well, you'll notice here that for the N-type material close to the metal here, right here at the surface, we doped it super heavily. So there's a lot more phosphorus atoms here than there are out here. What's that do for us? Well, remember, when you dope a diode heavily, the depletion region shrinks, right? So now my barrier is confined to a very thin region here. Now, remember from quantum mechanics that if I have a barrier and I have an electron, that it has trouble making it through the barrier, but if the barrier becomes very thin, then an electron can do what? It can tunnel through the barrier, right? And how we predicted that for an electron, if you remember, is that if you had a barrier and you have an electron, it had some sort of wave function for it, right? Well, if you looked at the wave function for an electron, as soon as the barrier becomes so thin that a portion of the wave function for the electron penetrates to the other side, that means that it's a probability that it could show up on the other side, and that's why I get tunneling. The key point, again, is that if this barrier becomes thin enough, I can tunnel electrons in either direction through this thing, and again, it will look like an ohmic contact because this no longer looks like a barrier. Here's a little bit of advanced stuff for this. Here's a listing of example material systems. Here's metals. Here's semiconductors. Okay, and so you're listing things like the metal work functions for them and barrier heights. There's a website where you can reference this. Here's a Schottky diode, which is a terahertz Schottky diode. That is blazingly fast. And so they used a Schottky diode to make this because they could use really great material systems to do this that you normally can't make p-n junction with, so they could use the ideal semiconductors they want. But the other reason they made a Schottky diode is that it's really easy to make, and therefore that's easy to make it really small. So why do I want to make the diode small? Well, if you look at the fastest you can drive any kind of circuit, you're often limited by the RC time constant, right? And so if I can basically make R low and capacitance low, I can get faster switching speed, right? Well, if I want to make my capacitance low, I need to make the area of the diode as small as possible. And so if you look at this device, here's one contact, here's the other contact. This contact goes down into this material, comes up here, and here's my diode right here. Here's a metal contact, here's this contact coming down the semiconductor, coming up right there. If I zoom in on this area, here's the metal contact making contact to the semiconductor down here. There's my Schottky diode. So they've made the area very small, which reduces the capacitance. And they've also worked hard to reduce the capacitance by putting a huge air gap here between these electrodes and these electrodes to reduce the capacitance there Furthermore, they've kept the electrodes separated this way to reduce the capacitance there. So they're working really hard to basically switch this thing as quickly as possible by reducing parasitic capacitances. A little bit more. In terms of Schottky diodes, some of the hottest material systems have traditionally been silicon carbide, but now gallium nitride as well. Both materials are hard to p-type dope, and so that's why you like to make Schottky diodes on these, because you don't have to do n-type p-type doping to make a p-n junction. And if you look at this down here, this is a diagram of what this gallium nitride Schottky diode looks like for high voltage rectification. It can provide, as it says, greater than 2400 volts of isolation, which is pretty amazing, and these are very high power. You could tell it's high power because the device here has got this metal heatsink, so it basically can dissipate a significant amount of power. When you look at the anode and the anode spreads out. This is on top of the substrate, so this is the metal Schottky contact. This cathode goes down into the substrate and makes contact to the semiconductor below the surface. And the anode has all these fins, and the reason why it has fins is that these things you can run so much current through these things that you want to spread the electrodes out so you get better heat dissipation. Furthermore, the corners are rounded because, remember, in electromagnetic fields, anytime you have a sharp tip will give you high field points, and that could cause, if I have increased electric field, I could get electrical breakdown, which is the topic we'll be talking about in the next lecture. Some advanced stuff, and we'll cover this again when we start looking at transistors. So I've showed you how to make p-n junctions. I've now showed you how to make metal semiconductor junctions. At this point in the course, it is important to note that you know everything you need to know to take any two metals, semiconductors, anything, join them together, no matter what materials they are, and you should be able to predict the band diagram. And then once you take into considerations of things we've learned, like drift and diffusion and barriers to diffusion and how bands shift with voltage, you could figure out how devices work. And so this is an example of doing that to make a high electron mobility transistor. I'm not going to describe how it works today, but in this case we're joining two semiconductors where I've got aluminum gallium arsenide that's heavily doped. I've got lightly doped gallium arsenide, which has a narrower band gap. And I've got all the terms I need. I've got the work function for the semiconductor, the work function for the metal. And so how do I do the band diagram for this? Well, again, it's all the same stuff. And so I know that the Fermi levels have to line up. So there's going to have to be this much shifting for the Fermi levels to line up, right? And so that means that this side basically has to go down, and this side has to go up for the Fermi levels to line up. And so I'm going to do that. You see I basically, when I join the materials together, this side moved up, this side moved down. Okay. The other thing is I have to do the exact same thing, maintain the offset where the materials actually join for the conduction band and the offset for the valence band. So in this case, this side is higher than this. So look right here where they join. This side is higher than the right-hand side. And down here, this side is lower where it joins than on this side. And so my offset, the left side is lower and the right side is higher where it actually joins. Then I need to basically fill in the gap. So if I shifted this up and there's my new conduction and valence bands, I need to basically then connect that with a smooth line which shows me where depletion and E field is, and I need to do the same on this side as well. The last thing I did to make this work well is I took into consideration that this is heavily doped, this is lightly doped, so most of the band bending is on the lightly doped side. There's very little band bending on the heavily doped side. Most of the depletion is on the lightly doped end side of this. So again, you can basically take any semiconductor and metal, semiconductor, whatever. You know enough now how to work with these and make any type of band diagram. Okay, so that's it for the first part of this lecture. Make sure that you can answer these review questions, and we'll move on to part 2 as soon as you are ready.